This video is about end behavior of rational functions, which is closely related to what a horizontal asymptote is. First, let's do a warm-up. Solve using the number line method. This is a polynomial. So we would put the critical points, -4, -2, and 6, on a number line. And then if I plug in really big numbers, I know that this is going to go off to infinity, so I'd put a plus. And then everything will switch except for at -2, where it's a squared, so it will bounce off of that spot. So I'm looking for where it's greater than or equal to 0. So I would put it at -4 and to the left, 6 and to the right, and then don't forget that at -2, the function does still equal 0. So the answer would be -infinity to -4 bracket union -2 with curly brackets union bracket 6 to infinity. Write the absolute value inequality that represents this solution. So the highlighted part of the graph, that absolute value graph would be where the absolute value of x plus 3 is less than 1. Now it might be less than or equal to 1. We don't really know for sure if that part is actually included, but it's at minimum less than 1. Could be less than or equal to 1 as well. We're going to talk about end behavior. So in the next few sections of the course, we'll be learning about something called limits, as well as practicing graphing rational functions. So we must figure out what the end behavior of a function is. In other words, what is the behavior of the graph as x approaches positive or negative infinity? The way that we do this is by considering the highest degree of the numerator and compare it to the highest degree of the denominator, just like we did in Honors Algebra 2. So let's take a look at these two curves. What we're looking for is the end behavior. To the right would be what happens as x approaches infinity. And the end behavior to the left would be what happens as x approaches negative infinity. And so as I look at both of these graphs, what I see is that as x approaches infinity, or x approaches negative infinity, I end up with the function r of x approaching 0. That's happening in all of these cases. Never actually equals 0, but it approaches 0 as we go off to infinity. We would also call this the horizontal asymptote of the function. So the horizontal asymptote is approaching 0 as we go off to infinity. So one thing we might want to be aware of is that the power of the denominator of the highest term, so the x squared here, is bigger than the biggest power on the top. Notice that it's bigger than 1 or bigger than x. That's something that we learned last year. Type 2, what happens if the powers are the same? So x divided by x, or x squared divided by x squared. If the biggest powers are the same, the end behavior, so as x goes to infinity or negative infinity, what's happening is that our polynomial is approaching some other horizontal line. So in this case, it looks like it's approaching 3. And in this case, it looks like it's approaching somewhere around 1.5. What we learned last year, and it's still true because the math hasn't changed, is that we can divide the leading coefficients, and that will tell us what the end behavior of the polynomial is as we go off to infinity or negative infinity. If the powers are the same, we divide the leading coefficients. So 6 divided by 2 is 3, and 3 divided by 2 is 1.5, 1.5, or 3/2. Notice that that's what our horizontal asymptote is. So in this problem on the left, as x approaches infinity or negative infinity, r of x approaches 3. And as x approaches positive or negative infinity in the one on the right, the function r of x approaches 3/2. Finally, what happens if the function has the power on the top bigger than the power on the bottom? Well, in that case, as x approaches infinity or negative infinity, we do not appear to have a horizontal asymptote. So in this case, and in this case, we ended up with an asymptote that looks like a slanted line. So the function r of x is not going to any particular number. In this case, the function goes to either positive infinity or negative infinity as it's going off the graph. So r of x, in both cases here, as x goes to positive infinity, the y values also go to positive infinity. And as x goes to negative infinity, the y values are going off toward negative infinity. So in summary, if the powers of the numerator are smaller than the denominator, the end behavior is as x goes to infinity or x goes to negative infinity, the function approaches 0. What we will start doing is we will start writing the limit as x approaches infinity of the function equals 0. That's new notation that's going to start happening very soon. So the limit of r of x as x goes to infinity or negative infinity is equal to 0. We would write a horizontal asymptote at y equals 0 for that part. When the powers are equal on the top and bottom, we divide the leading coefficients. So if I have a function in number 2, r of x, ax to some power, and that's the biggest power, over bx to that same power, what I would have is writing it in this new notation that we're going to start with, the limit as x goes to infinity of r of x is equal to a divided by b, or the limit as x approaches negative infinity of r of x equals a over b. So we just divide these leading coefficients. We would write the horizontal asymptote as y equals a over b. And again, that's something that we saw in these problems. A over b, 6 over 2, ended up equaling 3. So once again, this is what the end behavior notation would be. And if we translate that into the new limit notation, we would say the limit as x approaches infinity of my function r of x would be equal to 3. Finally, if the powers of the numerator are greater than the powers of the denominator, what we would say is the limit as x approaches infinity of r of x is equal to maybe infinity, maybe negative infinity, depending on how the graph looks. And likewise, the limit as x approaches negative infinity of r of x is also going to equal either positive or negative infinity, depending on how the graph looks. We don't really know. But there is no horizontal asymptote in these problems. It's a slanted asymptote, which we will start calling an oblique asymptote pretty soon. Finally, let's go over the 4 different types of things that we have if the numerator is greater than the denominator. So let's say I have something like x cubed over x. If I did long division on this, which I'm not going to do, in total, just in the interest of time, but if I did long division on this, I end up with x squared plus a bunch of other stuff. So this is going to kind of look like a graph of y equals x squared plus something else. And if I think about what the graph of y equals x squared looks like, my end behavior is going to go off to positive infinity for both things. So as x approaches infinity, or x approaches negative infinity, my function r of x is going to approach infinity for both of those. So I'm going to start writing it in my new notation now. So the limit as x approaches infinity of r of x equals infinity, or the limit as x approaches negative infinity of r of x is also positive infinity. Case 2, in this case, I have x to the fourth over x. If I did long division, it's going to look like x to the third. And so what you're starting to see is you can see if you just mentally divide the powers, the leading powers, you end up getting something like x squared. That end behavior is going to go up in both directions. X cubed, the end behavior, is going to go down to the left on the graph and up to the right on the graph. So the limit as x approaches positive infinity of r of x is going to be positive infinity, and the limit as x approaches negative infinity of r of x is going to equal negative infinity. If I do the same thing on the bottom two, what I'm going to end up with is, if I do some division on these two things, x to the fifth over x to the third with a negative here would be kind of like negative x squared. So my end behavior is going to look something like this, which means that if I do the limit, or end behavior, as x goes to positive infinity or x goes to negative infinity, that's not very good handwriting, it's going to be negative infinity in both cases. So I can kind of just think about what's going to happen as I go off toward infinity in these cases. If I divide these out, I end up with negative x. It's going to look something like this. So finally, I would do the limit as x approaches positive infinity of r of x would actually be negative infinity, and the limit as x approaches negative infinity of r of x would actually be positive infinity, or just infinity if you don't want to put the positive sign. Because as x goes to the left, the function goes up forever, and as x goes to the right, the function goes down forever.